Hello. Thanks for sticking around. I know the break is coming up, but I will hopefully give you something interesting to stay in the room for. So my name's David Wein. I'm a senior principal technologist at AWS. I've been there about 8 years, and I was the first principal engineer for a project that became Aurora Postgres, and now I lead something called Aurora Limitless Database, which we will talk about a little bit later. But I want to start by answering the question, why Postgres? And it's come up a lot this conference. I think everyone on this stage has talked about why Postgres. And I think it's the community. I mean, I have a couple anecdotes here. One is back in 2016, I joined AWS. I'd come from SAP at that point. I was working on HANA, and I ran into one of my architects from HANA at Sigmod conference. And he's like, hey, what are you up to? And I'm like, I can't really tell you what we're doing here, but I'm playing around with Postgres. He's like, why are you playing with Postgres? I'm like, just wait and see. It's coming. And I think we saw what was happening with the community. And I got that question again recently. It's like, why is Postgres so important and so vibrant? And why are we seeing so many startups, so much innovation? Why is it becoming kind of the lingua franca of the database world? Everyone's adding a Postgres interface or doing something like that. And I do think it's the community structure. I think it is the foundation nature of it, the fact that it is not a company. I have to correct people sometimes. They think Postgres is a company. It's not a company. It's not owned or controlled by any one entity, and has bylaws that prevent it from becoming owned or controlled by any one entity. And I think that is super important, and it gives a lot of people the confidence to keep working there. Now, when we talk about community, I asked one of my colleagues, because I work in the Aurora space, said, hey, what have we been doing with open source lately? I know we're doing a lot with contributions. And so one of my colleagues, Joe Conway, sent me some notes, and in his notes there was this picture, and there's a guy there that you might recognize. It took me a while. There was something different, and anyone notice the difference in this picture? No bow tie. This is pre-bow tie Bruce. So this is a photo of the very first Postgres core team. Bruce, what year is this? Do you know? 99. So, Postgres is driven a lot by volunteers and people that put in just the work in the community. And so thank you to all the community members who have done all that work. Thank you, Bruce, for your decades, really, of help. All right. So, what's going on at AWS and Amazon? So I think a lot of you know we've got a couple flavors of Postgres that we work with. We have our Amazon RDS, which is really a truer Postgres open source managed service. We have Aurora, which is our cloud native implementation. And then we really do have a Postgres community arm that we work on. So it took us a while to come around, but I think we've really gotten there in terms of Postgres commitment. So this slide shows the percentage of features that AWS contributed to each of the last 3 Postgres major releases. And so a little bit at 14, a little more at 15, but 19% of the features in Postgres 16 were contributed by Amazon. And that's made us the second largest contributor to Postgres open source. Thank you. Thanks Jimbo for having a lot to do with that. I think that's a lot. So we do think, community involvement is very important. I talked at the beginning about why Postgres, and that's it. So we're supporting this. We're now recognized as a major sponsor, and there's a lot of ways that we're involved. Whether it's helping on extensions or core things, there's a lot. There's beyond just code. There's reviews. There's design discussions. There's sponsorships and conferences. There's employing people whose full-time job it is to work on Postgres. So we have one Postgres core member at AWS. We have 6 committers, a major contributor, and 2 recognized contributors. There's a lot of ways that we support. You can, Postgres through things. And these are some examples of some of the things that we have contributed recently in Postgres, either from just direct code or review or design discussion. We also do bug fixes, even working in Aurora. From sort of inception, we've come across some weird cases. We run quite a bit of Postgres on behalf of our customers, so we see a lot of things, and we always contribute those bug fixes back as we see them back to the community and get them in. Here's just an example of a recent focused effort about community and partnership, even in the commercial space. Logical replication has been a major construction area in Postgres the last few years, and there's a big focus now on sort of filling out that story. And the partnership here between all these companies, it's not just one company that's driving this. This is a partnership across design, discussion, strategy, and code contribution, where all these companies work together to put features into the open source. Now, if you want to learn a lot more about this, you can hear from Jonathan Katz, my colleague who sourced a lot of this material for me. QR code to his talk on open source at Amazon from reInvent. All right, you're going to see during this talk, you're going to see a few slides like this. There's a lot of great content in the AWS reInvent YouTube channel. I'll throw a few QR code links up there, but really, if you want to learn more details and deep dive on some of these things, it's a great place to go for some additional training. All right, so I'm going to talk now about some of the recent innovations in Amazon Aurora. I think at this point, most of us know what Aurora is. It's a cloud-native, fully Postgres-compatible managed database service. Went GA in 2017, so it's been around for a while. Has inspired, it uses a decoupled storage and compute architecture with log-based storage, has inspired a lot of other systems in open source or in commercial space and other cloud vendors. So it's been a very successful design, and we're pretty proud of it. Not going to go through the basics, but I want to talk about some of the newer things that have come up there. So this is actually really exciting. We have Postgres 16 support on Amazon Aurora already generally available. And this is the 8th major version that we have supported in Aurora Postgres since its launch. Now, there was a lot of concern in the beginning with the Aurora project. I think people were unsure. Is this a fork of Postgres? It was not Postgres 9.6 when it came out. Are you going to stay current with the community? And we made a lot of very intentional design and code decisions back in 2016 timeframe where we said, look, we think that Postgres community compatibility is going to be very important. We think that's what is going to make customers happy. That's what's going to help drive customer trust. It's going to avoid lock-in. And so there were things that we didn't do in the product that we maybe wanted to, but we didn't do because we biased for compatibility. We knew some things were coming from the community, and we said, hey, we'll wait for those because then we'll have better compatibility. So each year we've been able to put out a new major version and stay current with the community. We follow the annual release cycle. We do the quarterly minor releases that track to the community. And then in Aurora, we also backport the CVEs that come out in the quarterly minors to older minor releases because that's, we release sub-minor patches with CVEs that we've backported. And we have what we call, long-term, should be LTS, long-term support releases. So we'll pick, for each major, we'll pick a minor version. Usually it's around the .4, .5 minor. And we'll say, we'll just support this till the end of that major life support in 5 years. And so like we've supported 11.9 since then, and we've taken every CVE that has come out from the Postgres community and backported it to 11.9. For the customers that really were on 11 and they wanted to stay there and not upgrade for 5 years, and they didn't want to change miners, we brought those CVEs back. All right, so that's enough on that one. Okay, new cool things, Aurora IO optimized. So our customers came to us and said, hey, we need more predictable pricing on IOs. And so we offer now an Aurora IO optimized storage type. It allows you to pay for just storage and compute and no IO charges for reads and writes. So you get very predictable billing. It also allowed us to do a couple things technically. So when you charge customers per IO, you have to be very careful about what code changes you make to avoid introducing additional IOs that might be built. And so there were some ways that we were held back from performance because we were trying not to increase the number of billable IOs. And so we're now able to offer better throughput and lower latency when you use Aurora IO optimized, mostly due to the IO batching that we're doing. So this is a way, flat pricing, no IO charging. We also introduced optimized reads. QR code, you can read a full blog post on it, but here we're using local NVMe storage as an extension of the Postgres buffer cache for temporary objects and a tiered cache. And I'm going to go into a little detail on how that actually works. So in Postgres, you have your shared buffers, which is your cache, right? And Aurora storage, and in Aurora we use EBS for temporary objects. And so when you have a temporary object, it's first in memory, it spills to disk, it goes out to EBS, and then it comes back when you need it. And what we offer is 2 times the memory of the host, we give you an EBS. All right, so we now offer optimized reads with NVMe storage on the host if you choose one of the D variants that has local disks. And if you use the standard I/O, not the I/O optimized like I just talked about, if you use standard I/O, we're going to use 90% of that local NVMe device and give you that for temporary objects. All right, so that gives you better performance. Temporary objects are things like you run out of work mem, maintenance work mem, you're doing sorts, you're doing index creates, things like that. So now you have more space for that and you have higher performance. So objects go back and forth. Now, when you're in I/O optimized mode, we'll use 2x your memory for the temp space, but we will also use the rest of it for a tiered cache. All right, so here's an example of how shared buffers works. So you have a page in cache, Postgres wants to read it, page is in cache, that's great. You're no longer using it, it's no longer in shared buffers, and you have to fetch it from storage, right? Okay, so with tiered cache, we use 4 times the memory of the host on the local NVMe to accelerate your cache reads. So we reserve a small slice, about 4% of your shared buffers as metadata for managing this data on the NVMe. So when you do a read, the first thing we do is we check the metadata, see if the page is in the tiered cache. If it's not in the tiered cache, we pull it directly into shared buffers from storage. So standard I/O, right? Doesn't stop at the NVMe device, goes straight in. All right. Then when you're no longer using that buffer and it ages out of cache, instead of just throwing it away, we will put it down on the NVMe device. And we do this asynchronously in the background, so there's no impact to normal cache eviction or getting a free buffer. Then, when you go to read again, we check the metadata, and if the page is in the tiered cache, it's able to service it directly from the NVMe and bypass storage. Now, these NVMe caches, they tend to have trouble with updates, and that gets really hard. So what happens when you change the page? Now I've got a version of the page that's in the cache, and I have one in memory. That's bad. So what we do is we simply invalidate the metadata All we have to do, which is in-memory metadata that we invalidate, and now that page is gone from tiered cache, it's no longer there. The current one is in the regular buffer cache, and then it will make its way back to tiered cache if it is evicted. All right. So just some examples. So these slides here, there's a lot of nuance in performance stuff. I always say if anyone gives you a direct yes, no, black and white answer on something performance, they're probably not giving you the straight story. Performance is always nuanced, and there's a lot of nuance behind this. So this is looking at a uniform distribution select over a range of data larger than the memory working set. I'm going to give you a link to a YouTube talk that goes into all the details on this. But the general idea is I have an 85 gigabit or gigabyte working set, and it's fitting entirely in memory. And so I get good latency here on the left-hand side. Now, if I take that working set up where it no longer fits into memory, my latency goes out to disk side instead of memory side. That's the distribution. And that's because it's coming from storage, not from memory. And it's 4 times the latency of in-memory read. Now, if I go even more working set, where I'm getting even less reads from memory, I'm further out on the right-hand side. So when we introduce the tiered cache and look at that 340 gig working set, what you see is you get more hits in memory, and you have this new peak that is not quite the in-memory, and but it's better than the storage side, right? So it's showing you a latency much closer to a working set that's in memory, and it's only 1.5 times higher latency, higher than pure in-memory latency versus 4x. All right, I'm going to speed up. All right, one other thing. With tiered caching and PG vector, hot topic, we see up to 9x times performance improvement when using tiered caching for this. All right, so Grant McAllister, goes to all these details. You can watch Grant's talk. Also going to throw out a reference to my colleague Tim Stokes, has a great talk on HA and DR. All right, I'm going to try to hit quickly, though, a really cool thing that we've been working on called Aurora Limitless Database. All right, so this is a managed scale-out solution for Postgres that goes beyond the write and storage limits of a single instance. Can do millions of commit transactions per second, and manages petabytes of data based on a serverless architecture. All right, I'm going to bypass this so we get to the technical meat. So just a quick overview of what it looks like. You have client application will talk to transaction routers, and those will talk to shards, and those will talk to storage. All the transaction routers are equal. There's no special coordinator or special leader or single point of failure on the routers. All right, this is fundamentally Aurora Postgres, so it's still Postgres wire compatible, it's parsers and semantics. It has a broad SQL surface area coverage, and we support some of the selected extensions. We have 3 types of tables we use in Limitless Database. A sharded table, which will be distributed across all the shards. A reference table, which will be present on each shard, and this is what you would use for common joins and infrequent writes, but something you want to join with your data frequently. And then standard tables, which are just not sharded at all. All right. I do want to get into, quickly, in the couple minutes I have left, one of the really cool things, which is the transactional consistency that we built into Limitless. So there's a talk this afternoon or later this morning from Cockroach on isolation levels, probably going to be great. And Bruce has a talk on MVCC, which is also probably going to be great. But I'm going to do a real quick refresher and just talk briefly about how we pull this off. So read committed transactions, show the latest data, committed data before your query began, and you have repeatable read, which shows the latest committed data before your transaction began. So our design goal is we wanted to retain these regular Postgres semantics in limitless database while scaling out and giving the performance that scales linearly as the system goes out. So Postgres snapshots, very simplified. Snapshots have a transaction ID. No transaction IDs, no transactions with transaction IDs newer than my snapshot are visible to me. And committed transactions with transaction IDs older than my snapshot are visible unless they were running when I started my snapshot. And Postgres does this by creating a list of running transactions at the time it establishes a snapshot. Very oversimplified version of how MVCC works. But that's really hard in a distributed system. So you can't coordinate and do a list of all the transactions across all the nodes because then it doesn't scale. You also don't know until commit time if your transaction is going to touch one node, touch many nodes. You don't declare it ahead of time. It's SQL. So there's all sorts of challenges here. And we have addressed this using bounded clocks. So there's something called Amazon Time Sync, which is available on EC2. All right? And it allows us to do transactions it allows us to use the time to do transactions, and it's unfortunate. I have some really cool stuff here, but I talk too much about, I guess, too much about open source. I guess, well. So what you can do is I'll be around, as we've got the AWS booth out there. If you want to learn about how we actually do consistent time-based MVCC across multiple systems with consistent backup and restore, where you actually get a transactionally consistent view, a transactionally consistent restore of your entire system, come see me at the AWS booth out there. All right, thank you so much.